Okay, hello everybody. So this time we are supposed to focus on causal discovery. And before that, let's just finish the material that we were supposed to cover last time, which is about causal inference and counterfactual reasoning. So last time I briefly mentioned the backdoor criterion and front door criterion for causal inference for identification of causal effects. And as you can see from the criteria, they are graphical criteria because you can directly verify whether they hold true by making use of the graphical representation of the causal process. So right here, I try to establish the connection between the graphical criteria, including front door and back door criteria, and the potential outcome criteria. So here, the first one, backdoor criterion, is related to the so-called conditional ignorability. Here, in the potential outcome framework, you have to consider this y small x as a random variable. And this is random variable to represent the causal mechanism or to represent the property of the structural equation model associated with the causal process from x to y. Because this y small x just means that means the random variable of y given the intervention on x to set the value of x to small x. That's why it's just about this causal mechanism. Right here, you can see, I think last time we verified this condition, and now let's have a look at the front door criterion. So this is the front door criterion. Z basically intercepts all directed pathways from x to y. What does that mean? So here you can see the ignorability, potential outcome framework. The criterion says, oh, y given small x and z is the same as y of small z. What does it mean? It means that if you are given z, then x will not directly influence y according to the causal mechanism, right? It's the same thing. And then what does this mean? This is the second condition. Remember, y small x is the causal mechanism right here. Causal mechanism from z to y right here. And this is one part of this random set of random variables right here. And the second one says the generative process of x somewhere here. So the first one is right here. Oh. So this is the causal process from z to y. Everything that is involved in this causal process. And the second one is including all those random variables that are involved in the generating process of x. And those things, the concatenation of those two things will be independent from the causal mechanism from x to z. As you can see from here, the causal mechanism from x to z is right here, right? So those three things, this thing, the causal mechanism from x to z would be independent from the remaining things. Although those two things, y as a function of small z and x may be dependent because of u. Right here, you can see u is involved in the first part in the generating process from z to y because u is part of the mechanism, right? And u is also part of the mechanism to generate x. They can be dependent. But here, as long as they are independent from the generating process from x to z, we say this condition holds true. So essentially, this is another way to put the front door criterion. So now you can see the graphical criteria and the potential outcome criteria are closely related. And in most cases, they are equivalent. Sometimes they could have some subtle difference. Okay. So people try to give a sufficient and necessary conditions for identification of causal effects with the graphical criteria. Here, I'm going to give a sufficient condition. So some very similar necessary and sufficient conditions were also given in the literature. They are slightly more complex. Here, let's have a look at the sufficient condition. It's very simple. Just say the following thing. The condition for identifying the effect of y of x on y given by the probability distribution of y given intervention x right here is that there exists no bidirected path between x and any of its children. By the way, here you can see we use a do to denote intervention. There exist other notations. For instance, Peter Svertis from CMU uses a set right here. And actually he used this notation earlier, but Pearl's notation do got more popular. Okay, so here this condition says there exists no bidirect path between x and any of its children. Now let's verify this. In example A, you can see, oh, there's a bidirect path between x and y. And by bidirect path, I mean the following thing. Right here, we have some random variable here, which is a common cause or direct common cause of x and z. So essentially, if there's a bidirect path, we say x and y are confounded in this sense. And here the same thing happens, and here you can see z1 is the child of x, and there's a bidirect path. The definition of bidirect path is the path consisting of only bidirected edges. So this is bidirected, this is bidirected. That's why we say between x and z1, there's a bidirected path. Now let's quickly verify this condition on the graphical representations. Here, you can verify that in all those examples, this condition holds true. Right here, x causes y, there's no bidirected path between x and y. And here, x causes y, x causes z, there's a bidirected path between z and y. And again, this condition holds true. Okay, so you can verify this condition. And as long as this condition holds true, we know that the causal effect of x on y is identifiable. And similarly, here you can verify, you can consider those examples, and in all those examples, this condition does not hold true. So it's not clear whether the effect of x on y is identifiable. Actually, fortunately, this condition is almost sufficient necessary condition. So in all those examples, actually the causal effect of x on y is not identifiable. And you can see bidirect pathways. And then in some cases, we can further benefit from additional constraints on the causal mechanism. For instance, here, in this case, we have z, x, y, and there's the bidirect path between x and y. So according to the previous condition, you can see we cannot say the causal effect of x and y is identifiable because the bidirect path, right? However, if you assume the system is linear, as you can see from this figure to the right, now the causal effect of x and y represented by the parameter alpha becomes identifiable. So this is the very famous, it's called the instrumental variable. Z is the instrumental variable. Here you can see how we can solve the problem. First, you can do regression. You can regress y on z. First you can regress x on z, then you can recover beta, the value of beta, and then you can regress y on z. Then the linear coefficient of regression would be alpha times beta, right? Although there is a bidirect path, we don't care because this path is not effective relative to z. That's why the linear regression coefficient is alpha times beta. You know beta, you know alpha times beta. That's why you can just recover alpha. So you can identify the causal effect represented by the linear coefficient in this case. However, in the general non-parametric case, it's not necessary to be identifiable. And the last thing regarding identification of causal effects is the definition of propensity score and how to use it. So let's consider this example. Here we have a lot of covariates, other features, and we have x, y. We want to identify the causal effect of x on y. And in the general case, we just use the probability distribution of y given to x to denote this causal influence. And you can derive the average causal effect or other measures by making use of this probability distribution. So now you can see this is right here. You can see the expression for this conditional distribution right here. you have to consider the average of probability of y given x and c. Here C contains the other covariance with a weight probability distribution of C of the covariance, right? So if you have randomized controlled experiments, this part, PC, in the two groups, you have the same PC, right? You have the same distribution for C. That's easy. However, if you don't have randomized controlled experiments across the control and the treatment group, probability distribution of C could be different. Actually, you are considering probability distribution of C given X. You could only discover this conditional distribution from the group. How can you just make use of the same distribution across the two groups? The two groups have different values of X, right? In one group, you have in the control group, right, X might be 0, and in the treatment group, X takes value 1. So you want to calculate this guy. How can you do this? We have to do something like matching. We have to match the distribution of C covariance across the two groups. And one way to do so is to directly match the distribution of the covariance. Usually, the covariance could be high dimensional. You can have a lot of other features, including gender, age, location, climate, and so on. It could be a lot of features. This is kind of troublesome because you have to consider, you have to match the distribution of a high dimensional vector. So instead of considering C, you can do something different, very different, by making use of the so-called propensity score. So what's propensity score? Propensity score is actually a random variable. It's a function of the covariance. It's defined this way. Propensity score is a function of C. Actually, is the probability for X to be 1 given C. Now you can see, since the value of X is given, this is just a function of C. Since C is the random variable, this HC is also random variable. So propensity score is a random variable. And you can show that given this guy, given this propensity score, X, the variable you intervene on, and C, other covariance, become conditionally independent. And because of this property, we say HC, the propensity score, and C are confounding equivalent in the following sense. Originally, we wanted to take the average of the mechanism probability distribution Y given X and C according to the distribution of PC, right? Distributions PC. We want to marginalize out C in this way. And after some transformation, you can see finally, we can just ignore C, but make use of H random variable propensity score HC instead. So here you can see equivalently, we just calculate the average of the distribution Y given X and H with the weight probability of H. H is compared to C, H is much simpler because no matter how high dimensional C is, H is just a single scalar variable. It's a function of C, but it's just a scalar variable. It captures all the relevant information in C relative to X, the random variable. Now this is much simpler. So this is why propensity score got a lot of applications in identification of causal effects. So instead of matching the distribution of the covariance across the two groups, you just match the distribution of the propensity score, which is the random variable across the two groups. And in particular, this random variable is very simple because it's just a scalar random variable. Okay. So finally, let's have a quick look at what we can benefit from the so-called counterfactual reasoning. Is there any question? Okay. Remember, so far we had a look at the two kinds of questions. First one is about prediction, right? You are given data. You want to make use of the conditional distribution implied by the data to make a prediction. So essentially, you care about some prop. Yeah. Questions? I heard someone say something. No. Okay. So this is about prediction. You just care about the data. You don't care about the causal mechanism at all in this simple setting. And the second question is about the intervention. You want to intervene on X2 and then see the effect on X3 according to the population. So you have a group of people, you want to see the intervention of X2 on X3 in this group of people. So the question is, would the person which is not specified, cough if we make sure that she or he has yellow fingers? So by make sure, basically we do that, we do intervention, right, to guarantee that's the case. And furthermore, we can answer the so-called counterfactual questions. So the question is something like this. Would George, a particular person, cough had he had yellow fingers, given that he does not have yellow fingers and coughs? So compared to the second question, you can see now first of all, we care about the effect of interventions had he had yellow fingers. And furthermore, we are giving evidence of the same unit or the same person we are talking about. So it's something like this. Giving the observation here as evidence, we want to see something about the same unit or same person under intervention right here. So compared to interventional effect, this question is more informative, more specific, because I have evidence about this particular thing I'm talking about. Let me just give an example to show what we can benefit from this way of thinking. Here, suppose X causes Y with this functional causal model. So you can see how X influences the Y. Here E is noise. And usually noise E is independent from X. Otherwise, we have a confounder. And once you consider confounder, again, the noise will become independent from other causes. So here, when we say X causes Y without the confounder, then the error term E would be independent from X. And now we find the individual with the specific values for X and Y, so small x and small y. The question is, what would Y be if X had another value, had been another value, say X prime? So let me give an example. Suppose X is, say, attendance rate. Let's talk about me. Suppose last semester I took some class. X is the attendance rate, and Y is the final grade I obtained in that class. So last semester, I had this X value for the attendance rate. I had this small y value for the final GPA. Now, I want to do some, I want to reflect what I did. I want to see what change I should make next time, right? I want to basically reflect my previous behavior. What can I do? I want to ask this question. Oh, last semester, if I were intervened to take the value of X prime for the attendance rate, what would be my GPA, right? So now, how can you answer this question? You may say that, oh, now X takes another value, X prime, then I can just use the best value according to the conditional distribution of Y given X, right here, right? As the answer. So this is the expectation of Y given X equal to X prime. You may say this is the best prediction. Yes, this is the best prediction, but this is not what we want. Here we have additional information. We know that we are talking about me, right? We know that I have some specific property. And when you do intervention on X, the particular thing, attendance rate of the class, my specific property will not be changed by that. And we can make use of that property. Okay. Xinxian, you have a question? Are you speaking? I cannot hear you.
Oh, sorry, I don't have a question. I just click on by mistake.
Okay. Okay, good. So now you can see what we can make use of the additional information compared to the regular prediction task. How? So intuitively, let me just make it very quick because we have to cover some other things. So essentially, this is the answer. How can we find this answer? Let me skip this. So this is a question. I want to see, this is just a shorthand for the long question. I observe this. X takes this value, Y takes that value, right? I already observed that as evidence. Now I want to see the value of Y, given intervention on X to set the value of X to X prime. So this value is different from the previous one. And I want to see the value of Y. This is the question. So we are talking about a particular situation or particular unit, particular person. And we observe this and we want to make a change and see the effect. That's it. So here you can see the general framework to solve the problem. Basically, the framework is as follows. Given the evidence, we have to derive the property of this particular person, of the specific property of this particular unit, represented by U. You can see U here represents the exogenous noise, right? For each person, for each unit, we have some, basically there's some noise. By noise, I mean those things that are not included in the model. And in the causal process, those things will influence the variable that we observe, right? So from the evidence, we can infer the distribution or value of the exogenous noise, and then we keep their value and change the value of X, and then we can do inference, we can do prediction. Here you can see the example. From XY observation evidence, we can see the value of E. Remember, E represents my specific property, which is independent from attendance rate. After I find the E, then I just set the value of X to X prime. And then I use E and X prime to find the value of Y according to the structure equation model or the causal mechanism. So we have this value. And this is exactly this value right here, indicated by the blue star right here. So you can see this value can be very different from the expectation of Y given X prime. Okay. Any questions regarding counterfactual reasoning? To summarize, with counterfactual reasoning, you can really make use of the specific property of the unit, right? If you talk about some particular event, you can just see the particular property of the event, and then you can make a specific change and see how this particular change influences the final outcome. Then in this way, you can do something like attribution. You can see, oh, for this event, what is the most important cause? And then you can do something to prevent that from happening next time. Or next time you can improve the result by making use of the important causes. Is it like taking advantage over this specific interval instead of a whole support for this example? Yes, roughly speaking, you're right. It's because if you talk about prediction, right, you have no idea about the noise. It's a completely random variable, which is independent from X, right? So if you talk about prediction, then the value of Y, given X takes value X prime, the value of Y can be anywhere right here, right? This is the condition. This will give rise to the conditional distribution of Y, given X equal to X prime. However, when we talk about a particular person, we have information of the noise. And given the information of the noise and the new value of X, you can immediately derive the value of Y, which is the answer to the counterfactual question we're concerned with. Isn't from Hashid, isn't PE given X independent of X? Oh, this is the no. PE given X is the posterior of X of E. Oh, there's some confusion. Let me go back to the slide. And then we will go back to the, we'll go to the next question. Right here. This is the distribution of the exogenous thing given evidence, right? This is nothing but the posterior. And in this particular example, where X causes Y with this functional causal model, from XY, we can infer the value of E, right? Of course, you can infer the posterior of E given the evidence. It's not the posterior given X, it's the posterior given the evidence. And here you can see, oh, E takes this value if I know the value of X and Y. Next question. Then why slow? Come on, window, please come. Okay, the chat window does not show up. Oh, now it comes. So next question is, how do you find out the most important causes using counterfactual reasoning? Okay, very good one. Now you suppose you have you consider two possible causes, right? X and Z. They are causes of Y. So X and Z causes of Y. Now you can, by doing this, you can see how much you can change, in Y by making certain changes in X and in Z, right? And then you can see which change will finally lead to more changes in Y. Or in some cases, you want to see which change in X or in Z can finally lead to the expected change in Y. That's why you can find the right cause to achieve your goal. Or you can find the right way to make a difference to achieve the expectation over Y, or to achieve the expected outcome. Okay. So please read the slide later. And I know this is very brief. And then let's talk about causal discovery and how to make use of some causal thinking to understand some machine learning problems. So basically, you can see a lot of examples in which we have to do causal discovery. And this is a very nice example published in Science a couple of years ago. So you can, the conclusion they gave is that the large-scale psychological differences within China can be explained by rice versus wheat agriculture. In other words, they believe that agriculture causes psychological difference within China. You can see in these kind of examples, first of all, you cannot really do intervention, right? You cannot really force people to change their agriculture. And second of all, even if you can do intervention, you have to wait really a long time to see the effect. That means it's not practical. So in many cases, it's not practical. In many cases, it's not impossible. So you have to discover the causal relations by analyzing observation of data, or by doing data analysis, or by doing machine learning. Here, basically, you can see how they infer the final conclusion. We have different random variables. We observe some dependence and the conditional dependence, and finally, under some further assumptions, we can draw the conclusion that S causes Y. This is another example. The data was collected by my collaborator, Marlene Nobeck. Her last name is very nice. Nobeck, just go forward. So she collected 8 variables of 250 skeletons all over the world. And those random variables include sex, location, diet, and a lot of properties of the cranial, of this part, basically cranial size and the shape differentiation and so on. So basically, they want to understand, as in archaeology, they really want to understand why people from different areas are different, look different. They want to see the reasons. And given this causal interpretation or causal given this causal understanding, they want to make a prediction into the future, right? In the future, maybe some condition will be different. Then how will the people, human beings, look like? And here you can see some other examples. In each example, we are given only 2 random variables. Basically, we are giving IID, observations of the random variables, IID draw from the distribution. And by analyzing the data points or the underlying distribution, we want to see which one is the effect and which one is the cause. And furthermore, you can derive the causal model from the cause to the effect. And in the last example, you can see this is the more complicated. So we observe XIs. We observe a lot of random variables, like the pixel values of images. And then we want to discover not the causal relations between the observed random variables. Instead, in most cases, we want to first discover the underlying causal variables, hidden variables. And the second, we want to see the causal relations between the underlying variables at the same time. So sometimes you want to derive the underlying concepts by analyzing the observed data, right? The concept could be color, shape, and so on. At the same time, you care about the causal relation between the concepts. So how can we make use of the machine learning techniques to discover this hidden world by analyzing observed random variables? And this has been, we have been doing this for 2 years. So our group, we have made some progress, and now I think some very interesting results will be published in the very near future regarding how we can estimate the hidden variables as well as their causal relations by analyzing the observed random variables. Okay, this is another more complex example. So traditional causal discovery methods fall into 2 categories. One is called constraint-based methods, and the other is called score-based methods. Later, you will see why we call them constraint-based and score-based. So in order to discover causal structure, or in some cases causal model, from statistical data or from observational data, we have to establish the connection between causal structure and the statistical properties of the data, right? So what assumptions can we use to establish such a connection? Essentially, it's about modularity. It's something derived from modularity. Remember modularity. When we say X causes Y without a confounder, without latent common cause, we mean the following thing. There are 2 generating processes, one for X, the other for Y from X. And the 2 generating processes are not relevant. They are completely irrelevant. You can change something here in the process from X, Y, and the other one will not be changed by that. And similarly, you can change the generating process for X, and the mechanism from X to Y will not be changed by that. So the world will consist of a lot of small modules, and those modules are not relevant. And then later you can see this will give rise to some statistical properties of the random variables. Okay, let me just mention one concept, which is the causal sufficiency. As you can see from the name, it's very intuitive. When we say the set of random variables is causally sufficient, we mean the following thing. Any direct common cause of 2 random variables in the set, V is also in the set. So here you can see if V is X, Y, Z, then it's causally sufficient because the direct common cause of X and Z, which is Z, X and Y, which is Z, is also in the set of random variables. And if V is only the set of X and Y, then it's not causally sufficient because the direct common cause of X and Z, direct common cause of X and Y, which is Z, is not in the set V. So it's very intuitive. Here you can see I use a direct common cause, right? And in most cases, the people just say common cause, and this is more rigorous. Here, Z is the direct common cause of X and Y. But even if Z is only the cause of X, you can see Z is the cause of X, and since X causes Y, Z is also cause Y. So in some sense, you can say Z is a common cause of X and Y, even if Z is not the direct cause of Y. That's why that's not rigorous. So let's just use the direct common cause. And then we define confounder as hidden direct common cause of 2 random variables. So if Z is missing, Z is not included in the set of random variables we are considering, then we can say that Z is a confounder in this relative to this set of random variables. Okay. So previously in Eric's lecture, I think you got to know that deseparation implies conditional independent relations according to the Markov condition. Basically, if X and Y are deseparated in the graph, then according to the global Markov condition, we know that X and Y are conditionally independent given Z. However, this is just a one-directional relationship. We want to go back to the graph, right? So we have to find some conditions so that we can go back. Otherwise, if you consider counterpositive of this Markov condition, we can see the following thing. If they are not deseparated, then X and Y will be deconnected. This means you can always find a trivial solution to satisfy Markov condition. You can always use a fully kinetic graph, right? Because for a fully kinetic graph, you cannot see any conditional independent relationship according to the Markov condition, right? And if you see the conditional independent relationship in the data, basically that can happen by accident. You don't care. So with the fully kinetic graph, Markov condition will always hold true. However, the fully kinetic graph is not informative. We want to find a graph which is minimal and informative and can be used to explain the relations in the random variables. What can we do? So we have to find another condition in addition to the Markov condition. What's that? Essentially, for this type of method, we have to assume faithfulness. Here, the faithfulness assumption is something like faithfulness in the relationship. So I'm faithful because I have a unique mapping, right? There's a one-to-one correspondence between something. Here, it's the same thing. Markov condition says that each random variable is questions. Okay, maybe you can mute. Maybe, let me just. I cannot mute you. Okay, good. Thank you. So Markov condition said that given graph, we can see independent relations or conditional independent relations. So each random variable is independent from non-descendants given its parents, or according to the global Markov condition, which is equivalent to the local Markov condition on DEX. It says if they are deseparated, then they are conditionally independent given the separation set. Now we can go further. We can go back by making use of the faithfulness assumption. It says that all observed independence or conditional independent relations in the data are actually entailed by the Markov condition on the graph. That means there are no extra or fake conditional or accidental conditional independence relation in the data. If you see conditional independent relation in the data, then this relationship must be the property, must correspond to the property of the graph. Okay, this is rather strong. And sometimes you can test this condition is testable. And in some cases, it's not testable. If you want to see more detail, talk to me after class. Okay, so here you can see some cases where the faithfulness assumption is violated. We have three variables here: health condition, risk of mortality, healthy lifestyle. So you can see we can have two causal pathways from health condition to risk of mortality. And if A equals minus BC, then this guy, although a cause of the final effect, will be independent from the final effect. They are independent because A equals minus BC. The causal effects got cancelled out. And similarly here, swimming skills could be independent from the risk of drowning, given there are two causal pathways, and given that the two causal pathways just got cancelled out. So in those cases, we have a violation of faithfulness. But generally speaking, this condition should hold true if you have enough data. Why? Again, this is because of modularity. Consider this example, right? If this is really a good description of the underlying causal process, then we have a modularity condition, which says that this module right here to generate healthy lifestyle would be independent from the generating process from those two variables, those two random variables, to the risk of mortality, right? They are different causal modules. And those causal modules are independent, meaning that they involve the parameters were chosen by nature independently. There is no way for them to be related. They are not coupled. So if they are independent, then the chance for you to have the condition that A equals minus BC is basically has measure 0. This is the justification for faithfulness based on modularity. However, if you have finite data, right, they may be close. A can be very close to minus BC, and you cannot really distinguish, you cannot really verify whether A is minus BC or not, given you have finite data. So because of that, some people assume strong faithfulness. So A has to be significantly different from minus BC in order to derive something about the causal structure given data. Now, faithfulness just eliminates such possibilities. As a consequence, you can see whenever I see those random variables, then I'm sure that healthy condition is not independent from the risk of mortality because they are the causal path between them. As long as they are the causal path, they cannot be independent because you cannot see the independence from numerical condition on the graph. Now, we can just have a look at the two types of methods for causal discovery. First, let's have a discussion. First, can we find the skeleton of the causal structure? By skeleton, I mean the undirected graph. So if there's a causal, if X is the direct cause of Y, then there's the edge between them. For now, let's just ignore the arrow, ignore the causal direction. We just want to find the skeleton. Can we find the skeleton from data, right? And the second thing is, suppose we have the skeleton, then can we find the direction between random variables? Yes, we can do something. First, you can show the following thing. Given Markov condition and the faithfulness assumption, then you can show that two random variables are adjacent in the causal graph if and only if they are dependent conditioned on any subset of the remaining variables. It also means that if X and Y are conditionally independent given any subset of the remaining variables, then they are not adjacent. This way you can find the adjacency, right? So this is the answer to the first question. And the second question is about whether we can find the direction in some cases. The answer is also yes. Right here, in this corner, you can see, suppose we have three variables, X, Y, Z. And again, suppose we have a causal sufficiency. For now, let's assume we have a causal sufficiency. There are no hidden direct common cause of two variables. Now, suppose we observe the independence between Y and Z. And this is the only independent relationship regarding X, Y, Z. They are independent. Then you can see that this is the only possibility to explain this independence. Y and Z are causes of X. And this is known as V structure, right? You have a V structure here. So now, with the same skeleton, you may have some different causal structures, as you can see from here, right? And those three possibilities have very different conditional independent relations compared to this one, right? For this structure, Y and Z are independent, and for the remaining three possibilities, Y and Z are not independent. And furthermore, you can see that Y and Z are conditionally independent given X. They are different. So in this case, we can discover the unique structure given that Y and Z are independent. And we can go further. We can determine the directions for more edges according to the orientation propagation. Now you can see how we can solve the problem. First of all, you want to do independence test in some specific way to determine the skeleton or the adjacency between random variables. And then you find the V structure, and then you can do orientation propagation in the following way. So here you can see an example. We have 1, 2, 3, 4, 5 random variables. We observe data. From data, we can find the independence or conditional independent relation. Suppose we have a reliable procedure to infer independence and conditional independent relations. First, in order to achieve data efficiency, we start with the marginal independence. So first, we test for marginal independence without the condition on any random variable. So you can see here, any pair of the random variables is conditionally dependent. So we cannot remove any edge. We start with this fully connected graph, fully connected undirected graph. And then if we condition on a single random variable, you can see, oh, A, C independent given B, A, E independent given B, A, D independent given B, and A, C, and D are also independent given B, right? And given this, we know that A and C are not adjacent, and E are not adjacent, and D not adjacent, and so on. As long as they are conditionally independent, given anything, they are not adjacent. And then we increase the size of a conditional set. Now we condition on two variables. And then you can see B and E are conditionally independent given C and D. then we can remove the edge between B and E. And then you cannot go further because you cannot condition on more random variables, given some constraints, because here we have to condition on a subset of the adjacent variables. It's not necessary to consider other variables, and they are the proof for this. And this is the PC algorithm. And before the PC algorithm, there was another one called the SGS algorithm. SGS stands for Peter Socrates, Clark Glimmer, and Richard Shines. In that algorithm, you do conditional independent test between each pair of the random variables given any subset of the remaining variables. And later in PC, this procedure was refined. You only need to condition on a subset of the adjacent variables, and you can show that that's enough. Okay, now after the first step, we find the skeleton right here, and then we can find the V structure. Here, C and D are independent given B, right? And they are not independent given E or given B and E. Then we know this is the V structure. C, D, E will form a V structure. They are independent given something else, not this guy. Okay. So in the previous example, we don't have B. That's why the two random variables are marginally independent. And we know, oh, this is a V structure. But you can have other variables as common causes of C and D, or as intermediate variables between C and D, doesn't matter. This is still a V structure. And then you try to go further, right? Unfortunately, in this example, you cannot go further. You cannot determine any other causal direction. This is the PC algorithm. Step A, you initialize this graph with a complete underailed graph, and step B, you just find the skeleton. And in step C, you find all V structures from data. Basically, you consider all those triples, and then all those triples with this pattern, and then you test. You see whether X and Z are conditionally independent, given a subset of random variables which does not include Y. If that's the case, it's a V structure. If that's not the case, it's not. And then you do orientation propagation. What does it mean? Here I give two examples. In total, there are only four rules, and they have been shown to be complete. Basically, you can only find such information. There's no additional information you can make use of to discover the direction in the causal graph. The first one is to avoid spurious V structure. So after you find the V structure, you can see this direction, and this is. Questions? Hi. Okay. So here, I know the direction for this edge. I don't know the direction for this edge. Then for this edge, the direction must go this way. Otherwise, we are going to have a V structure, right? And we know this is not the case, because if this one were a V structure, we would have found it in step C. And right here, we have the rule called away from cycles, because we assume the underlying causal structure is a DAG. So here we have this direction and this direction. Then for this one, it must go this way. Otherwise, we have a cycle. Of course, you can see you may say, oh, this is not reasonable. You made so many assumptions. Yes, you are right. And later there exist other methods in which we can avoid those assumptions, including acyclicity and causal sufficiency and other assumptions. So basically, we are able to discover the true causal information in very general situation right now with suitable methods. How can we represent? Okay, questions. Is the away from cycles example in the example, isn't a spurious V structure created? Okay, let's go back. So here, if you have this edge, right? If you go this way, then this is not a V structure, because for those three variables to form a V structure, two of them, right? There must be exist one pair of the random variables which is not adjacent. As you can see from here, in this example, X, Y, Y, they cannot be adjacent. If each pair is adjacent, then definitely it's not a V structure. Good. So now you can see in some cases, we have some information of the causal directions, but in some cases we have no idea. That means we cannot use the DEC to represent the final output of the algorithm. What can we do? So first, we can define some equivalent class. Two DECs are independence equivalent if and only if they have the same skeleton and the same base structure. Okay. And then we can only recover such an equivalent class from data by making use of conditional independent relations. And such an independence equivalent class can be represented by the so-called pattern or CPDEC. CPDEC stands for completed partially directed cyclic graph. Here you can see an example. So some edges are directed and some edges are not. If they are not directed, it just means that the causal direction could go either way. Okay, so the interpretation is rather simple. If you have this, then we have this direct edge. We know that in each possible solution, which is a DEC in the solution class, the causal direction must go this way all the time. And if you have this undirected edge, we know that, oh, in some cases it goes this way, and in some cases it goes in the other way. And in this case, we know that they are not adjacent in any member of the equivalent class. This is how you can interpret the result. So in this case, in this example, how many DECs do we have in the equivalent class? So clearly it's 2, right? Go this way and go this way. Okay, so now let me give another example. In the slides, you can see some more examples, but now I just want to make it more brief. So we are given data, as you can see from here. And from data, whenever needed, we can discover independence and conditional independent relations. And then we can find the causal graph in the following way. First, we find the independence between x1 and x3. Then we can remove the adjacency, remove the edge between them. And then when we condition on single random variable, we can see independence between x1 and x4, given x2. That's why we can get rid of this edge. And similarly, we can get rid of the edge between x3 and x4. And then we can find that x1, 3, and 2 form a V structure because 1 and 3 are independent, and they are not independent, conditional independent given 2. So they are independent given something else. And then we know this is the V structure. And then we can go further by making use of the first rule. Right here. This one, for this edge, the direction is determined. And this one is not determined, right? Then the edge must go this way. Otherwise, we have a fake V structure regarding x1, x2, and x4, right? And then the dependence pattern or independent pattern would be totally different. So the edge, this edge must go this way. So in this case, you can determine the causal adjacency and also the causal directions of all causal edges. You can see some examples. I gave a couple of 5 examples in the slides. I would say, let's skip that, given the limited time. You may want to have a look afterwards. Okay, so you can see from data we can make use. We can do independent test and conditional independent test. We can find the direction, and sometimes you have some background information, and then you can refine your result. And this way, by doing data analysis, you can really find something novel compared to the domain knowledge. Okay, now let's have a look at this case. You have 4 variables, x1, 2, 3, 4. You observe from data, you discover the independence between 1 and 2, and the conditional independence between 1 and 4 and given 3, and independence between conditional independence between 2 and 4 given 3. Now, can you just apply the previous procedure to find the causal structure? Maybe you can do this as an exercise right now. So 1, 2 not adjacent, 1, 4 not adjacent, 2, 4 not adjacent. Then you can find the V structure. Then you do orientation propagation. What result would you have? Yeah. So the result, basically, we already talked about this example. 1, 2 not adjacent, 1, 4 not adjacent, 2, 4 not adjacent. V structure here, and then we have this orientation. We can determine the direction between 3 and 4 I make use of orientation propagation. Okay, now the question is, do you think it's possible at all to have a confounder behind X3 and X4? Is it possible? No, it's not possible. Because if you have a confounder here, right? C here as a common cause, direct common cause of X3 and X4. Now you can see if you have C here, then if you condition on X3, X1 and X4 will not be independent, will not be conditionally independent because we have a collider or common effect here, X3. If you consider this path, let me just if you have a confounder here, see, now you can see, oh, when you condition on X3, this path will be open, meaning that generally speaking, X1 and X4 will not be independent, conditionally independent given X3, right? That's not the case. So we cannot have a confounder here. It's not possible. And that's why this is called a Y structure. If you have a Y structure, then you know that right here, it's not possible at all to have any confounder. And this had a lot of applications. You may read this slide later. So this is the real application. You can really determine the causes of biomass of the plants in this example. Okay, I'll skip it. Now let's have a look at another example, some other examples. Basically, I should put it this way. This is very simple, and in our daily life, in many cases, we make use of this rule or this observation to infer causal relations. Here, as long as write something down, we have ABC, right? And we have a condition. Suppose we have a conditional independence between A and B, A and C given B, and then we have ABC. As long as this is not the case, as long as B is not the cause of A, then we know that given they are conditionally independent, we know that we can determine the causal direction between B and C, and we can further infer that there are no confounder between them. That means, B must be a direct cause of C. Why? This is because if A is the cause of B, or if they are the common cause for A and B, then the direction between B and C must go this way, right? Otherwise, you have a collider, B is the collider, then A and C cannot be conditionally independent. So we have this direction must go this way, if this is not the case. Let's consider some examples. In the first example, let A be rain, B be slippery ground, and C be the chance of falling down. So given B, A and C are independent, we know B is not the cause of A. That's why we know slippery ground, it must be a direct cause of falling down. And you can apply this way of thinking to many other examples. Even in history and culture, you can really determine causal relations this way. Of course, we just take independence and conditionally independent relations as input. In many cases, you may want to have a lot of data points, or you may want to resort to some domanology to verify whether we have independent or conditionally independent relations between random variables. Okay. Now let's have a look at another example. So here again, we have 4 random variables, x1, 2, 3, 4. We have independence between 1 and 3, and between 1 and 4, and between 2 and 3. Now, can you just work out the example? Work out the solution. Again, I give you 20 seconds. They are not adjacent, they are not adjacent, they are not adjacent. Then you want to find a V structure. Okay. So here you can see basically 1 and 4 are not adjacent, 1 and 3 are not adjacent, 2 and 3 are not adjacent, right? And then furthermore, if you apply the PC rule, you can find a V structure. X1, 2, 4 will be a V structure. Why? It's because X1 and X4 are independent, right? They are marginally independent. Then we have a V structure here. So this guy must go this way. We have a V structure. If there are no confounder, we have to go this way. And similarly, 2, 3, 4 seem to form another V structure because 2 and 3 are independent, marginally independent. And here, of course, we can make it more general. You can always condition on some other variables, right? Now you can see, oh, there's some problem. So the contradiction. 4 causes 2 and 2 causes 4. What does it mean? Why do we have this phenomenon? This is just because there must be some confounder behind X2 and X4. And you can even go further. We have a confounder, and there cannot be any direct causal influence between X2 and X4. Because if there are any, then now you can see X2, suppose we have a causal influence from X2 to X4. Then X2 and X1 and X4 will not be independent because eventually X1 has a causal influence on X4 right here. Okay, so we can see in some cases, we are sure that there are no confounder. And in some cases, we are sure that there must be some confounder. And similarly, you can apply this way of thinking to infer confounders and to the causal discovery, even in your daily life. So here, let X1 be whether I'm sick. So let's consider events. X1 is I'm not sick. X2, I'm in class. X3, you are in class. X4, you are not sick. Now you can see basically X1 is independent from X3. 1 is independent from 4. So you can verify those conditions. And then you can see that, oh, there must be a confounder behind X2 and X3. Meaning that the fact that I'm in class does not cause that you are in class. Both of us are in class because for some other reason, which is the confounder. What's that? It's a schedule, right? It's a class schedule. Okay. So, and those things, those rules we just talked about were integrated in the fast causal inference method. And fast causal inference method does not assume causal sufficiency, and also it allows a selection bias. Basically, you can see some extra dependence relations caused by selection bias. And the result produced by FCI is asymptotically correct, even if they are confounders or selection bias. However, one thing that the causal process over the measured variables, if you have confounder, right? Over the measured variables is not necessarily a DAG anymore, right? As you can see from here, if you have error, latent variable here, if you observe error, then this is a DAG. You have a DAG to represent the causal mechanism over the five random variables. But if error is hidden, you only observe 4 random variables. Now the causal process over the 4 random variables, xi's, cannot be represented by a regular DAG. What can we do? We have to use another thing called the PAG, partial ancestral graph, to represent the output of FCI. And clearly this is more complex than pattern. For pattern, we just have a directed edge and undirected edge, or absent of the edge, right? Only 3 different possibilities regarding the relationship between 2 random variables. Now we have, in total, we have 5 possibilities. And here, it means X1 and X2 are not adjacent. And here, we have circle here. It just means that, by the way, the circle means the following thing. If you observe a circle, that means right here, we can have an arrowhead or arrow tail. That means if it's the tail, then that's the confounder. If the tail, X1 is the cause of X2. If it's the head, then they're the confounder. So finally, it means X2 is not the ancestor of X1 because we always have arrowhead here. And similarly, here we can, in this case, we have two circles. And then it just means that there are no set to deseparate x1 from x2. And if you observe this, we say x1 is the cause of x2. And if you see this kind of edge, we say there's a latent common cause, there's a latent direct common cause for x1 and x2, or there's a confounder for x1 and x2. Okay, so the algorithm of FCI is rather complex. I'm not going to talk about the detail, but as long as you can integrate, you can interpret the results, it's fine. So here, by making use of these different patterns, you can just interpret the result by FCI. Okay. Any questions? No. Okay. Let's go further. I will spend 2 minutes on the score-based method. As you can see from this illustration, we just consider different causal graphs, and then we see which of them will give the best score, right? Sometimes we want to search for the best DAG, and sometimes we want to search for the best equivalent class represented by a pattern. And for causal discovery, in most cases, we just directly search for the best equivalent class because we cannot determine the unique DAG by making use of data in most cases under the traditional assumptions. So this is GES greedy equivalence search. This score is assumed to follow some properties, which include score equivalent, locally consistent, and decomposable properties. And then you can use the BRC score for the search. Then it was shown that if you have enough data, then finally the search procedure will give you the best, the optimal solution. So it's asymptotically correct. The search procedure consists of two phases, which are the forward greedy search and backward greedy search. This is the kind of very regular, very common thing in machine learning, right? If you want to find a Markov equivalent, sometimes you have to do this. You add random variables, and finally you get rid of unnecessary random variables. It's the same thing. Let me just use examples to illustrate the procedure. So suppose this is the underlying causal graph. We have x, y, z. X, are common causes, XZ are causes of y. Then first we may find this edge. Suppose this parameter, in the linear case, suppose this parameter is very large, and then we find this edge. At the same time, we know that this is a weight structure because every time we just search over the space of equivalent classes when you use GES. Here you can see another example. For simplicity, suppose all those causal edges have positive effects, and suppose all edges have the same parameters. Because here I assume it's linear. Then you can see that it's very likely to have this edge in the first place, this one, between x and y. Why? This is because the correlation between x and y might be very, very large because of the multiple paths between them. So you have this one in the first place, and then you have the other edges. And then that's why you can see we have to make use of the second step, which is to remove unnecessary edges. Now you can see, oh, this edge is not useful at all, given we have those edges. Then you can get rid of this edge and find the right equivalence class. Okay. So just now you saw the classical method for causal discovery. Now let's just spend several minutes on the new methods, and later you can just read the slides. It's not possible to cover every detail. So we can go further. If you use the classical methods, essentially it's an inverse problem. The causal structure gives rise to the conditional independent relation in the data. However, the mapping is not one-to-one. That's why you cannot, in most cases, you cannot recover the unique structure. And in particular, if you have only two random variables, traditional methods can only say whether they are independent or dependent, right? You cannot say whether x equals y or y equals z, or they are the confounder. What can we do? You have to make use of stronger assumptions regarding the causal mechanism, and then all of a sudden, you can see more information about the causality. So here you can see the problem setup. We have data pairs, we have observational data for 2 random variables, and the question is whether we can find the causal direction between them. And fortunately, we can. So by making use of functional causal model, we can. A functional causal model is just a mathematical way to represent the effect as a function of the direct causes and the noise. Right here, y is a function of x and e, and if there are no confounder behind x and y, x and e would be independent. Okay, this functional causal model. Here you can see some typical functional causal models, well-defined functional causal models, with which we can discover causal direction and the causal models. Before this, let me just give a remark. If you don't have any constraint on f, then given any 2 random variable x and y, you can always represent one of them, say x, as a function of the other variable and independent noise. You can always construct such a function. However, if you have constraints on the function, this is not the case anymore, as you can see from the slide in 1 minute. So the first one is the linear non-Gaussian cyclic model. Effect is the linear function of the direct causes and some independent error term. And this is called additive noise model. We have nonlinear function. Actually, this assumption is still very strong because in most cases, the noise is not really additive. So this is another model called post-nonlinear model. We developed this model a long time ago to solve some real problems. And this, you can see this is more general. We'll see examples later. So in the linear case, we can easily go from correlation to the asymmetric causal relation. If we assume the variables, or if you assume the noise terms are non-Gaussian. Here you can see an illustration. I generated x first, and then I generated y. So basically, x causes y in this way. And then in the first row, you can see the Gaussian case, where x and e are both Gaussian. You can see the scatter plot, and then I try to explain y with x. By doing linear regression, I regress y on x. This is the regression line, and here you can see the scatter plot of the residual and x. And you can see the same thing in the reverse direction. I regress x on y. You can see in both cases, the error term is uncorrelated from the predictor, and also they are independent, because in the Gaussian case, independence is equivalent to uncorrelatedness. Right now, you can see another example at the bottom. So in this example, x and e follow the uniform distribution. If you regress y on x by linear regression, you can see you just recover the original causal process. The residual will be independent from x. However, if you regress x and y by doing linear regression, you can see a very different pattern. Right now, this residual is first of all uncorrelated from y, because whenever you do regression by construction, the residual is uncorrelated from the predictor. They are uncorrelated. However, clearly they are not independent. As you can see from here, the distribution of residual given y will change across different values of y. So they are not independent. This means that in the wrong causal direction, the error term is not independent from y, although they are uncorrelated. So you can see a lot of examples. Basically, more generally, we have the linear non-Gaussian acyclic causal model. Linear non-Gaussian acyclic causal model. So you can just write down a set of equations, structural equation models, or equivalently, you can have a graphical representation with the parameters. And in matrix form, we have this x, the set of or vector of observed random variables, is a linear transformation of itself plus some independent noise. In this matrix representation, all diagonal entries are just zero. Basically, each of them just represent a self loop. If you have non-zero entry here, just means that x1 will influence itself, right? For simplicity, we assume there are no self loop. Then all diagonal entries are zero. And the problem is how you can recover this matrix from data. So generally speaking, we have this matrix form to represent the causal relations. And the problem is how you can recover this structure from data. If you assume all noise terms or disturbances, EIs, are non-Gaussian, and also they are assumed to be mutually independent, if you assume there are no confounder for now, then we can recover the DAG uniquely by making use of the connection between this linear non-Gaussian causal model and independent component and independent component analysis, ICA. Here you can see a high-level idea. So right here, you can just rewrite the causal model. Then you can see, oh, with a specific linear transformation, the components of E will be independent. And the ICA applies the linear, giving observed random variables xi's in the random vector x. We apply linear transformation W to make the outputs as components of Y independent. So both of them aim to produce independent components. And both of them use linear transformations. And then if you find W with ICA, with some specific operations, you can recover the information of B. Okay, I'm going to skip this, but maybe you can read this later. And you can show that the solution is unique. Because if the underlying graph is the deck, then there's only one way, only one solution to B, given the W. Notice that the solution to W is not unique, because no matter how you permute the rows of W or rescale the rows of W, you do not change the independence relations between the components, right? Between the components Y. However, if you go from all those W's to B, although the W solutions might be different, the solution to B is always the same. Okay, this is the ICA. I'll skip this, and let me just make the final remark. You can see why ICA works and demonstration. And in particular, please read this. In practice, most variables are non-Gaussian because of Kramer decomposition theorem, which is kind of complementary to central limit theorem. This is very important. This is why we can make use of non-Gaussian method or non-linear method. And okay, finally, let me just show a single slide. I have to skip all those things. So in practice, we have to consider a lot of issues, including nonlinearities, mixed categorical and continuous random variables, memory error, selection bias, confounding, missing values, temporal information, and non-stationarity or heterogeneity of the data. So basically, all those problems have been tackled in some way, although a lot of work needs to be done, especially to solve the problem of confounding. And the problem of discovering latent variables as well as their causal relations can be considered as a specific problem to deal with confounding. And okay, I have to skip this. Maybe you want to read the slides. So to summarize, we care about the causality because if you want to change something, you really have to make use of causal representation, and you can do causal inference. By causal inference, I mean two things. You can identify causal effects, and you can do counterfactual reasoning to explain a specific event, a specific phenomenon. By making use of different types of independence, we can do causal discovery. With conditional independence, we can develop the constraint-based method or traditional score-based method. And with independent noise condition, in the functional causal model, we can even find a causal asymmetry between two random variables. And as a consequence, you can recover the underlying data uniquely from data under some assumptions. And you can make use of independent changes in non-stationary or heterogeneous data to find the causal orientation and also causal edge. And in practice, we have to find very good solutions to the problems of confounding, selection bias, and we have to find a way to make use of temporal information and so on. And also, some machine learning tasks, including transfer learning, depends on how you can make use of the property of the joint distribution of the data, right? Maybe you have to combine or leverage different distributions of the random variables, or maybe you have to find a connection between different distributions and so on. So in all those problems, it seems that causal view provides some useful guidance as to how to solve the problem, because eventually you want to find a compact representation of the changes in the distribution. And this is consistent, or this is something like modularity, right? Modularity tells you that all those modules are independent, even if they change independently. And finally, you can find a good representation of the change of the distribution, and then you can make good prediction, even in those very complex situations. Okay, thank you. Sorry, I'm running late. Okay, if you have questions, please stay. Otherwise, you can leave.